Okay, so we are going to discuss the solubility equilibria and solubility constant in this video. We learned that the ionic compounds can be divided into two based on the solubility, soluble compounds and insoluble compounds. There are exceptions, but we are talking about the insoluble compounds here. These ionic compounds that are termed insoluble actually have a very low but definite solubility. Okay, so the saturated solution of these insoluble compounds or the salts are another type of equilibrium, and that's what we are going to discuss in this video. For example, let us see Ag2CO3, that is according to the solubility chart, that is going to be insoluble and it will stay as solid. In the same way, we can write AgCl, that is also solid, which is insoluble, correct? But when you put those compounds in water, let us see how is that going to AgCl solid. Let us see how is that going to dissociate. It will dissociate into Ag plus ions, which is going to be AQ because we just said that it got very low solubility, correct? So it will be Cl minus AQ. So we know how to write the equilibrium constant K for this equilibrium expression K for this dissociation. Okay, so we will write products over reactants, correct? So the products are Ag plus, we don't have to write the state symbol, Ag plus and Cl minus. And we will not write the reactant here because we know that solid state will not appear in the equilibrium expression. So we can write the same way for Ag2CO3 as well. How are we going to write Ag2CO3 dissociation? That is solid state changing to, there are two Ag, so I will write 2Ag plus AQ plus we have CO3 2 minus, that is also the state symbol is going to be AQ. How are we going to write the equilibrium expression K equal products over reactants? And we will write Ag plus, and we have a coefficient of 2 here, so to the power 2, and CO3 2 minus. And we don't have to write the reactants again. So that's how we are going to write the equilibrium expression. But since we are talking about the dissolution of the insoluble salt, we are representing this K with a special character, that is we are going to put a subscript SP. Okay, so we call that one as solubility product constant. So that means the equilibrium constant for a chemical equation representing the dissolution of an ionic compound is the solubility product constant. So what is that? S represent is the solubility and P product. So we will write that one as KSP. All right. Okay, so we can see the KSP chart here. For AgBr, we will have a constant that is 7.70 times 10 to the power negative 3. And for AgBrO3, there is another value here. Ag2CO3, we have another value. That means for each compound, the KSP value is different at that specific temperature, correct? And we were talking about Ag2CO3 and AgCl now. And you can see the KSP values here. But can we compare it directly? Actually, we cannot. The reason for that one is this is going to produce 3 ions as we have seen, 2 Ag plus ions and 1 CO3 2 minus ions, so total 3 ions. Whereas in AgCl, we are having only 2 ions, 1 Ag plus ion and 1 Cl minus ion. So we cannot compare these KSP values directly. But can we compare the AgBr and AgCl? Yes, we can, because AgBr is also going to give you only 2 ions, Ag plus and Br minus. So that means 2 ions here and 2 ions in AgCl, correct? So we can actually compare the KSP values of AgBr and AgCl just by looking the KSP values here. We can compare that. So which one is lower here? We can see that AgBr is the lower number, 10 to the power negative 13, we can see. So that means what? The smaller KSP value indicates lower solubility. So solubility of AgBr is going to be less than solubility of AgCl. And now there are four types we are going to discuss to write the KSP expression, and we will see what is molar solubility means. Okay, so let me say the first type, which is 1-to-1 ratio. What is that means is it will give you two ions when it dissociate. So AgCl we have already seen, but let us write one more time. That is a solid. AgCl will give you Ag plus Aq and Cl minus AQ. So we know how to write the rice table and all, right? So normally we will put X when it dissociate. For solid, we will not write anything. And we will have X here, correct? And then how are we going to write the K expression? K, in this case, we have to write SP as a subscript. So KSP equal, we know how to write the K expression, the products, and we don't have to write the reactants. So what is the concentration of Ag plus as per our step here, which is x, and this is x, so that means x square. Okay, so we can directly substitute that x value. So what is that x value is the concentration, correct? That concentration is the solubility of that Ag plus and Cl minus, so in moles, okay, in moles per liter. That is called molar solubility. Okay, so that is molar solubility. So we are connecting KSP and molar solubility now. So if you know the KSP, you can calculate X value, correct? And vice versa. So now we can see another example, BaSO4. So how are we going to write the dissociation? Let's see that. BaSO4 is solid state. When you dissolve that one in water, the slight solubility makes it to dissociate into barium ions and sulfate ions. So how are we going to write the K expression? KSP equal concentration of barium ion and concentration of SO4 2 minus ion. So we can write this one as X, this one as X. So we will get again X square, right? So whenever there is 1-to-1 ratio of ion, we will get that one X square. That is KSP equal X square. We can directly do that even without doing the rice table, correct? If it is just direct question like that, we will discuss different types though, okay? And now let us see another type, which is 1-to-2 ratio or 2-to-1 ratio. What is that means? It can be PbCl2 and another example can be Ag2CrO4. And also we can see that Ag2CO3, just now we discussed that one, right? So in general, we can say AB2 or A2B form. Okay, so how are we going to write the KSP? Let us see. Let us take the example of PbCl2, which is in solid form, and it will dissociate into Pb2 plus 2Cl minus. In order to balance this Cl2 here, we have to put a coefficient 2 here, right? So both are in aqueous state. And we can write the KSP equal Pb2 plus concentration of Pb2 plus times concentration of Cl minus to the power 2. How we will write this one in X terms? Let us see that. Pb2 plus is X because only one ion there, and we have 2Cl minus, so we will write 2X. So what I will do, I'm going to substitute the concentration. So concentration of Pb2 plus is X. So I will put X here. Concentration of Cl minus is 2X. And I know there is a superscript 2 here. So that means it should raise to the power 2. So how is that going to be when you solve it? So X times 2 times 2 is 4 and X to the power 2. So we have 3. We can see that X 3 times, so that means 4x to the power 3. So we will write KSP equal 4x to the power 3. So let us see another example, Ag2CrO4, that is in the solid form. So when you write that dissolution, we have 2Ag plus Aq plus 1CrO4 2 minus. That is also going to be Aq. So what are we going to do here? Again, we can write in terms of x, 2x, and this is going to be x. So we can write KSP equal concentration of product, which is going to be Ag plus to the power 2, and concentration of the other ion, the anion CrO4 2 minus. And we know Ag plus concentration is 2x, and we have a power 2 here, and for CrO4 2 minus we have x here, so that equal, so 2 times 2 is 4, and x to the power 2 and x. So what we will write again? 4x cube. So you can see that whenever there are 3 ions forming, we can write 4x cube to connect with that solubility product, correct? So Ag to CO3 already you have seen that also. Let us revisit and let us write that Ag to CO3, which is solid form, and we will write 2Ag plus AQ plus CO3 2 minus AQ, correct? So in terms of x, this is 2x and x. We can write KSP equal to, the products, let me write that one first, Ag plus to the power 2 and CO3 2 minus. And now in terms of x, we can write Ag plus concentration is 2x to the power 2 because there is a power 2 here, right? So then it is going to be x. So that means we will have 2 times 2, 4x square from this one and x from here. So that means 4x cubed. So whenever you have 3 ions, you can directly write KSP equal 4x cubed, right? Okay, so let's see another type, which is 1 to 3 or 3 to 1 ratio. One example is AlCl3. So let us go ahead and see that one, how to write that one. AlCl3 solid form. When it dissolved in water, we will get Al3 positive Aq, and the anion is going to be, we have 3 chloride ions, correct? So in terms of x, I can write this is x and this is 3x. And now let us write KSP expression in terms of the anion and cation. So the cation concentration times the anion concentration to the power 3, correct? So that means we have seen that cation is x and the anion concentration is 3x, and we have a power 3 here, so we have to write 3 here. That means x times, we will have how much? 3 times 3 times 3, that is 27 x cubed. So we have 4x here now, so 27x to the power 4. So you will get the same expression if you have another type called, if it is AB3, it's going to be 27x to the power 4, and if it is A3B form in general, we will also have the same form, KSP and X relation. All right. Now let us see the last type that I want to explain is A2B3 or AS2S3 type. Okay, so that is an example here. So this is AS2S3 is one example, and ZN3PO4 ties is another example, which shows 2 to 3 ratio, or it can have another compound with a, I can say, A3B2 type. So that is also 3 to 2 ratio. The total ions formed will be 5. Let us go ahead and see that. So let us take an example of Zn3PO4 twice, which is solid, correct? We will get 3Zn2 positive plus, and we will have our anion 2PO4 3 negative, both are in AQ form, correct? And now we can write the x expression, that is 3x here and 2x here. And then what I will do, I will write the KSP expression, concentration of products, Zn2 plus to the power 3, concentration of PO4 3 minus to the power 2. And now in terms of x, we can write the concentration of Cn2 plus, we got it as 3x. So we will be writing 3x here to the power 3, and for PO4, we have 2x, that's to the power 2. So what we will write, 3 times 3 times 3, so 27x cubed, 2 times 2, 4x square. So you will get 108x to the power 5. So if you are taking another example, you can find the same. And you can try some examples. Now, why can't you try AS2, AS3 by yourself and see whether you are getting 108 to x to the power 5. Okay, these are some general form how to write the KSP expression, some examples.